Uh, okay, my office hours will still start as usual, Friday 8:15. I will be on Zoom, and you have quiz 7, 8, 9 due next week. That's based on the lecture we do today or last time too. Okay, now we have three basic counting techniques that we need to learn, three basic counting methods that we need to learn. The first one is fundamental principle of counting. We also call that counting principle. It actually has a lot of other names, fundamental theorem of counting, counting theorem, counting techniques, a lot. But here I will use fundamental principle of counting. Now, the thing is, of these three tools, these three methods, there could be some confusion when to use which one. So the way I will do it is I will do it this way. So for example, when I discuss fundamental principle of counting, I will break it up into 4 steps. The first one, the situation. Fundamental principle of counting, the situation starts with that we have 2 boxes or 2 categories or 2 groups. Box 1 has M items and box 2 has N items. Second thing, what do we do in this situation? The action. We will select 1 items from each box. Let's say, for example, I have 1 box containing 4 pens, and then another 1 box containing 6 erasers. Forgive my examples. If you use pens, you don't use erasers, I know. But imagine that from the first box, I will select 1 pen, 1 out of those 4. And from the second box, I will select 1 eraser. Now, the question is, how many possible outcomes? Possible outcomes. Or in this case, how many possible different pairs? Now, how many choices we have from box 1? If you have 4 pens, then we have 4 choices, right? And for each choice we have for the pen, we have 6 choices for erasers. So the total is 24 possible outcomes. Now then, finally, what's the solution? The solution will be M times N, as we can see in this example. Now that's the basic idea, okay? Now this is supposed to be an easy situation where you can select the items one by one, one from the first box, another one from the second box, another one from the third box, and see how many possible outcomes. Now, if you wonder how we get this 24, why do we multiply that? Then we may want to see how the selection was done. First, when we select one pencils, there are 4 possible choices of pencils, of pens. Okay, call that pen number 1, pen number 2, pen number 3, and pen number 4. Now, for each choice of pen you have 6 possible choices of erasers. Eraser 1, eraser 2, eraser 3, eraser 4, eraser 5, eraser 6. Now imagine if I copy paste this to all pen choices. Like for pen 1, I have 6 choices. Okay, for pen 3, I also have 6 choices. And for pen 4, I also have 6 choices. So in total, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so on and so forth. And the final one is 24, option number 24. Okay, now that's the basic idea. Let's do some more problems, but I hope you can find this to be on the simple side. I will select problems from some other textbook. Let me see. Give me a second. Suppose, for example, this one here. I wonder if you can see it. Can you see that now? A grocery store has 5 brands of crackers and 4 different varieties of cheese. For this example 2. How many ways can Josh select 1 brand of cheese and 1 brand of crackers? Solution. How many choices of cheese does Josh have? 9, that's right. And then for each brand of cheese that he chose, how many choices of crackers he has? 5, that's right. So 9 times 5, and in total, then he has 45 ways to choose 1 brand of cheese and 1 brand of crackers. Okay, more problem. Let's say I pick to get another picture. Give me a second, okay? Where's my picture? Example 3. Professor Okamoto selects 3 students to report on 3 different current events. If there are 28 students in the class, how many ways can Professor Okamoto make the selection? Now let's see. Solution. So the first choice. How many choices this professor has for the first choice? So he will select one of 28 students, right? So, I mean 3 of 28 students. So the first choice, this professor has 28 students to choose from. And then, after he chose that student to report one event, then how many choice he has for the second student? There will be only 27.
27.
And then for the third student, that will be 26. Okay, then you can use calculator to compute this. This is 28 times 27 times 26. That gives me 19,656. Now, when you do your work in my quiz or my test, I need you to write this first. How you get that before your calculator work. Okay, so for this one here, I need you to write this first before the 19,656. Is it okay? Now that's for example 3. Let me give another example. I think this is a type of example I usually give in class. Suppose I have a 7-digit phone number, or maybe PIN. Let's talk about PIN. An ATM PIN consists of 4 digits. And then my first question, how many pins possibly be? How many pins are possible? If there is no restriction whatsoever, then the way we think, okay, there are 4 digits I need to fill up, right? Okay, the first place, how many choices do I have? The first choice, I have 10 choices because I have 0, 1, 2, all the way to 9, right? So I have 10 choices for the first place. How about the second place? Now there's no restriction, which means that I may be able to reuse the number I used earlier, right? Okay, so for the second place, I still have 10. For the third place, I still have 10. For the fourth place, I still have 10. So in total, I have 10 to the 4, or 10,000 pins possible. Okay, now part B. Suppose I change the question a little bit. How many pins are possible if no repetition allowed? We still have 4 places to fill up. Okay, the first one, we have 10 choices. And then the second one, I have only 9, because I cannot use the number I already used earlier, right? Okay, if the first choice I have 10, then that choice will be taken away. Then I have only 9 choices for the second, and then 8, and then 7, which when I multiply, I get, yes, 5040. Now, let's go on even further. Suppose I ask how many pins are possible if no repetition and the last digit is odd. Now, in this situation, we will work on the box or the position that has the strictest requirement first. In this case, we start from the last digit. How many choices of numbers we have so that the last digit here is odd? We have 5 choices. Now then, from that 5, we can choose any one of these 3. Let's say I start from the first one. I already used one odd number at the end, right? Okay, so how many numbers I have, how many choices I have left for this first choice? And then 8 here, and then 7 here. Okay, which when we multiply it, we will get 2,520. Now, again, if I ask this question and I give you 3 points for, let's say I give you 3 points for part C, then I give you only 1 point for this and 2 points for this. Okay, so in the end, don't say, oh, Thomas, I get the same answer with my friend, but why you deduct me 2 points? Now, wait, is it 3,600? I don't think it's 3,600 though. Okay, 7 times 8 times 7 times 5. Yeah, 2,520, okay? Yeah, but what I said earlier is I need you to show the work more than just the calculator work. Probability, especially for the counting part, tends to be on the easy side at the beginning until it gets mixed up. Okay, so please learn to show the work because that's really how you think in step by step. Now that's for the first part. Let's go on to the second part, which is permutation. The second part, permutation. Now, what is permutation? Let's see the scenario, the situation. You have one box or only one category with n distinct item. And the action, what we will do in this situation, we will select R items from the box. Now, of course, because there are only n items, then the number of items I can select from there must be less than or at most equal to the number of items available. And order is important.
Baby, stop. No.
Okay. Now then, this the question. How many possible permutation?
What are you target shortcut?
Iris, would you mind to mute your microphone?
Are you doing that? Sorry.
How many possible permutation or arrangements? Possible. How many possible permutation or arrangement? And the answer will be the solution is NPR. Okay. Now I will teach you how to use this calculator, this on your calculator very soon. But let's see an example first. For example, I have five different letters. Let's say those letters are A, B, C, D, E. Now this makes sure that they are distinct letters, right? And then we will select a code, a 3-character code, 3-letter code. Consider that like we are selecting a password of 3 letters from these 5 letters. Okay, and the question is how many codes possible? How many 3-letter codes possible? Now the answer will be, the solution will be 5P3. 5P3. Now this 5 and this 3 are subscript. This N here and this R here are subscript, which means it is written lower and smaller. Okay, now the thing is, how do we use calculator to compute this 5P3? How do we use calculator to compute this 5P3? Let me bring up my calculator. Can you see my calculator right now? Now to compute 5P3, I will press 5 first. Follow me with your calculator. I will not repeat this. 5P3, 5 permutation 3. I'll press 5 first and then go to math here, math. Now you see the red color there, the red button, math. If you see this red means that's the last button I press. And then we move from this math here, we move the cursor to PRB. I'll move the cursor to PRB. Everybody with me? Now, anybody not with me? Okay, now once you get PRB, then you move the cursor down to that NPR. And then you press enter. And then after that you press 3 and then press enter. Okay, this is 5 NPR 3, which is equals to 60. So going back to our node, and 5P3 equals to 60. Is it okay? Let's do more problem. Let me pick problem from other book. Let me see. Give me a second. Okay, let's say, for example, this one here. How many arrangements of 3 people seated along one side of the table are possible if there are 8 people to select from? So you have 8 people, okay, and then you want to select 3. You want to select 3. Now the thing is, they use the word arrangement, okay, which means it's the order is important. Now then from there we think, okay, then I have 3 places to fill up. Okay, I have 3 places to fill up. You can do this using a counting principle. So the first place, 8 times 7 times 6. Okay, but if you do it that way, you will see this result here is the same to if we do 8 permutes 3. You have 8 people, 8 items, and how many ways can you order or arrange in order 3 of them? That will be 8 permutes 3. Now, can you use your calculator to compute this? The result should be the same to 8 times 7 times 6. Somebody say 336. Okay, I just need to make sure that you know how to use your calculator. Let's go back to my calculator view. I want 8 permutes 3. Enter. 336. By the way, do you see my calculator view?
Yes.
Okay, good. Because what happened, there was one time I actually moved to another view, but on my computer, but it turns out that's not what my students see. So please, when I ask that question, I want an update from you. Okay, now let me go back to my paper here, my notes. That's my example 2, I believe. That's 336. Maybe I write a note here, which is a very good news for us. Note. All permutation problem can be done using a fundamental principle of counting. Okay. Now I saw somebody make a comment about TI-30. For this time, you still can use TI-30. Yes, Berenice actually shared with us if you use TI-32S, then use PRB, and then move the cursor to NPR. But you need to type it in that order. You type 8 first, so you type 8 first, and then NPR, and then 3, and then enter. Okay, because TI-30 works the same way with TI-83 or 84. Okay, but we will need TI-84 very, very soon. I think the earliest I can, next week we need to use TI-84 already. Okay, so please have that right now. I mean, within this 1 week. I think I told you already since the first day of class though. Okay, so try to get it as soon as possible. Now let's do more problem to show you that yes, every permutation problem can actually be done using fundamental principle of counting. Let me pick another example. Let's see. Give a second. See that. Oh, 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 oh. My system. Give a second. I want to remove this. Here, and then make it larger. Okay, let me ask you to take a look on that question first. For this example, 7 paintings are exhibited by art students. Part A, an art appreciation class is asked to rank the paintings 1 through 7. So there are 7 paintings. How many different rankings are possible? If we try to use fundamental principle of counting to do this, then rank number 1, there are 7 choices. Rank number 2, there are 6 choices. Rank number 3, there are 5 choices, and so on and so forth. Okay, now, but if we use permutation, then we will use 7 permute 7. Okay, 7 permute 7 is equal to 5040. Can anybody else confirm that for me? I'll use my calculator. 7 permute 7. Yes, that's right. That's 5040. Okay. Now, how about part B instead? About part B. Can you try to work on that? If the students are asked to rank only the top 3, only the top 3. So of 7 students, you want to pick only 3 of them, and you put them in order. So according to fundamental principle of counting, this is 7 times 6 times 5 only, right? Which I compute, that's 210. However, if I use permutation, if I use permutation, this is 7 permutes 3. Which, if you use your calculator, should come up the same. Okay. Now, one of the key situation here is that we need to select from the same group. So this is the same group of 7 paintings. Okay, and we will select one by one, and the order is important. Okay, we'll select one by one, and the order is important. Actually, once we know the order is important, then it must be done one by one, right? Now, from the examples I show you, especially in example 2 and example 3, example 2, oops, sorry, in example 2 and example 3, I hope you realize something important. Note that 8 permutes 3 is the same to 8 times 7 times 6. The first number, that 8, means you start from this 8. And the 3 here, the subscript 3 here, represent the number of factors you start from 8 to 7 to 6. So 8 permutes 3 means start from 8, and then 2 factors after that, a total of 3 factors down. Now, likewise, you can see in part B here, 7 permutes 3. 7 permutes 3 means you start from 7, okay? And the subscript 3 here implies you have 3 factors down from 7. We can still use that idea here though. 7 permutes 7 means what? 7 permutes 7 means I start from 7 and then multiplied by one number less, multiplied by one number less, and a total of 7 numbers here. Okay, this is a total of 3 numbers. So for a little shortcut, suppose one day I ask you, okay, what is, for example, what is 12 permutes 2? You can use your calculator, but because it's small numbers, 12 permutes 2, then you think, oh, okay, I start from 12, and I just need 2 factors, right? I start from 12. Okay, and then I need 2 factors. So I need to multiply 12 by 11. And that's it, because I just need 2 numbers here. Which is equal to 132. Okay? Yeah, of course, you still can use calculator. But it's, in my opinion, because the number is small enough, if you can do it mentally, go ahead. Can anybody do this then? How about 5? No, make it 7 permutes 4. Either you use calculator or you use multiplication. If I do multiplication, what number do I start with? I start with 7, that's right, and then 6, and then
5,
and then
4,
and then
3.
Are you sure? How many numbers do I need?
Oh, not just 4.
Yeah, down to 4 only. Okay, down to 4 only. We stop at 4. That's right. Okay, I start from 7. I start from 7, and I go 4 numbers. 4 numbers. Okay, so this is equals to what? 210 times 4, that's 840. Yeah, of course, if the number gets larger, you may be better just use calculator. Okay, now those are the easy parts. The hard part is actually the third one. When it comes to combination. What is combination? First, what is the situation? Situation is the same to the situation of permutation. You have one box with n distinct items. Our action is we will select R items. Order is not important. Because I select R items from that n, then the number of items I select must be at most only n items. Okay, and because the order is not important, then regardless we take it one by one or not. Okay, because the order is not important anyway. Then part C, what's the question? How many combinations possible? But if they use the word combination, it seems to be too easy. Instead of using the word combinations, they may use the word how many group possible. How many sets possible. Okay, because inside a group, if I say that I take a group of 3 students, for example, then it doesn't matter who comes first, right? In other words, the word group does not have any sense of ordering. The word set also have no sense of ordering. And the answer will be the solution, how many groups possible, how many sets possible. The solution will be N, C, R, N combination R. Now let's say, for example, this is my favorite example actually. Let's say, for example, let us having a set of 5 letters, A, B, C, D, E. And then we want to select 2 letters, regardless the order. The question is, how many sets of 2 letters possible? Now, according to our discussion earlier, then the solution here will be 5, because there are 5 letters, and we need to select 2 of them. How many different groups of 2 possible? There will be 5 combination 2, which when we use our calculator, that will be 10. Now let's see how to use our calculator. 5 combination 2. It's very, very similar to 5 permutation 3, 5 permutation 2. Very, very similar. I start with punching 5. Now, for the combination, it's in the same group with permutation. I go to Math, PRB, and then choose NCR. And then 2, enter. That's how I get that 10. Okay, so the way I punch the calculator will be, the calculator punch will be 5, and then go to Math, go to PRB, and then NCR, and then enter, and then press 2, and then enter. Okay, 5, then Math, PRB, CR, enter, and then press the R, in this case is 2, and then enter. Okay, now that's the 10 possible sets of 2 letters. Now, we will practice more on how to use calculator to compute these combinations, but that's something easy. You can just watch the lecture video later on, or the one on YouTube, or you watch, I do it again for other type of questions later. But here's the thing, what are these 10? When we say, oh, there are 10 sets of 2 letters possible, what are these 10 though? What does this 10 implies? It implies there are 10 sets of the 2 letters possible. And those are, let's list them, AB, AC, AD, AE. So far so good? These are 4 sets of 2 letters possible. But we have more though. How about BA? Is BA counted? The answer is yes if the order matters. But in this case, because it's a set of 2 letters, so it doesn't matter the order. That's why then I will cancel this out, because this is the same to the set of AB. Okay? Now, and then BC, BD, BE, and then CA, but hold on, CA already counted. CA already counted here. And then CB, oh, CB already counted also. CB already counted also. I wrote that. I should try E. Okay, and then CD, CE. Finally, DA already counted, DB already counted, DC already counted, DE is not counted yet. Now, so those 10 refers to these 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are the 10 we talked about. Okay, now of these 3 counting techniques, the harder one, but the one showing up the most in our daily life is actually this type, the combination type. What I'm about to do right now, I will show you why this combination becomes difficult. this combination becomes difficult is mainly because we can apply that into a lot of different situations, but the underlying idea are exactly the same. So you will see the cases that I give you in this example 2, example 3, and example 4, they seems to be very different, but then when we think about that further and deeper, they turns out to be the same question to this example 1. Now, let's start with example 2. Example 2, suppose we have, there are 5 points on the circle. Let's say there are 5 points on the circle. Okay, I'll use this point 1, point 2, point 3, point 4, point 5. And then I continue. A chord can be drawn between any two of those points. So let's say, for example, this is a chord. This is a chord. Okay, we can do more. This is another chord. Now the question is how many chords possibly drawn? Now you may say, oh, I will just draw it one by one, Thomas. Okay, go ahead, you draw one by one. 3, 4, 5. Am I done? How do I know I can stop? How do I know I can stop? How do I know that I'm done? How do I know that I'm not missing any possible line? So that's the weakness of doing it one by one. Okay, so we will use the following idea. Here's the idea. Every chord takes how many points? Every chord takes how many points? Every chord requires 2 points, right? Takes 2 points. So the number of chords we can draw depends on how many different combinations of 2 points we can get. Because every chord takes 2 points, right? Every chord takes 2 points, then the number of chords equals to the number of ways we can pair those 2 points of those 5 points. So if I name it A, B, C, D, E, then it goes back the number of chords we can draw depends on how many pairs of 2 letters I can draw. Okay, A, B, A, C, A, D, A, E, B, C, B, D, B, E, C, D, C, E, D, E, right? Then how many are there in total? That would be 5 combination 2. There are 5 items. How many ways can I select 2 of them? 5 items. How many ways can I select 2 of them? Okay, and then when we use our calculator, you will get this is equals to 10. Now, you compare this example with example 1. In example 1, I use letters. In example 1, I use letters. I have 5 letters. How many set of 2 letters I can get? Then you say, Thomas, why do we play with letters? It's not really what I do in my life later on. Okay, then how about example 2? And then somebody else may say, oh, Thomas, that's geometry. I'm not doing math for the rest of my life. Okay, fine. Then how about we apply this to some social science? There are 5 people shaking each other's hand. How many handshakes happen? Then if you think about it, the number of handshakes will be 5 combination 2 also. Because each handshake takes 2 people. If you have 5 people, then how many ways can I get a group of 2 different people? That will be 5 combination 2, and there will be, therefore, 10 handshakes also. Okay, now what makes this combination difficult, especially because, and it's actually also applied to other cases, fundamental theorem, counting and permutation, that we are not really looking at the example and only use the same example all the time. We apply that to different cases. A, B, C, D, E, geometry, handshakes, and suppose, for example, those who like to play basketball, for example, there are 5 teams in a competition. They need to play each other. Once. Okay, now the question is, how many games should be done? Well, you will see the same thing, because every time you have a game, how many teams play? Each game takes 2 teams, right? So there must be 5 combination 2 games being played. That's 10 games. Okay, so there are a lot of possible variations, to the point that I once said to my other class that I can give you 100 examples today, and next week I give you another 100 questions that you never seen before. Okay, but all of them have the same underlying idea. Now let's do more problems. This time I will pick problems from other textbook. I don't use our textbook right away because our textbook goes to the probability right away. Now I want to focus on the counting for now. Give me a second. Say this one here. Students are to answer 4 or 5 exam questions. In how many different ways can the questions be answered? According to our technique, our solutions later on. How many different sets of 4 questions we can solve if we are given 5 questions? That would be 5. Choose how many? 5, choose 4. And when you use your calculator, that would be that would be 5. Okay, let's see. Just to remind ourselves how to use that calculator. I have 5 math, ERB, NCR, 4 is equals to 5. Okay, so this is equal to 5. Oops, I already wrote it down. Now, but if you think about it, what are those 5 times? Yes, there are 5 different ways, but what are those 5? Now, imagine if I have these 5 questions. Let's say question number 1, number 2, number 3, number 4, number 5. One way to do it, one way to answer only 4 of them is to select this 1, 2, 3, 4. So 5 questions I do number 1, 2, 3, 4. Now somebody else may say, you know what, I don't want to answer number 1, 2, 3, 4. I want to answer 1, 2, 3, 5. Or 1, 2, 4, 5. But answer number 1, number 2, number 4, number 5, and so on and so forth. Apparently, I hope you start seeing a pattern that in this case, we can say it's basically how many ways can you choose which question not to answer. So to choose 4 of these 5 questions to answer is the same to choose which question not to answer. So you see, the answer I don't, and the question I don't answer in the first method is number 5. The second method, I don't answer number 4. I don't answer number 3. I don't answer number 2, I don't know, 1. Okay, so basically there are 5 ways to select 4 questions out of 5 to work on. Let's go on. Suppose I do one more. This time you do it. This time I do it. I would like you to do it. Give me a second. The next example, Black Hawk Tech gives 4 presidential scholarships. If there are 50 nominees, how many ways can the scholarship be awarded? Give me the notation. How many people we choose from? From 50? How many people should we choose? We choose 4. Okay, so and using our calculator, you try it. I try to. I get 230,300 ways. Now again, when you show me the work, I need you to show me this first before you show me this. Okay, I need you to show me how you get that. Let's go a bit further. It gets more interesting now. It gets more interesting now. I will try to put probability into this. Suppose I have a Venn diagram. Suppose I have a Venn diagram. And let's say in set A, I have 5 people and not A, 7 people. So how many people in total? 12 people. And of these 12 people, let's say we have 5 of them getting an A. Okay, now suppose I say select 3 people of these 12. 3 people at random. And the question is find the probability that all 3 are from A. Then the way we do it will be as the following. We will select 3 people at random. Okay, what is the probability 3 people, all 3 of them from A? Then we will compute the number of ways you can get 3 from A divided by the number of ways you can get 3 of 12 from the whole set. Now, how many ways can we select 3 people from A? There will be 5 combination 3 over how many ways can we select 3 people of the total of 12. There will be 12 combination 3. Now, 5 combination 3 is 10, I believe. And then 12 combination 3 is 220. Which if I reduce, I get 1 over 22. Now, if you think about it, you can see it this way though. You can see it this way. We actually have two groups here, the one from A and the one not from A. The one from A, there are 5 of them. The one from not from A, there are 7 of them. Okay, a total of 12. A total of 12. Now, what is the probability if I select 3 people, then I get all 3 from here? Now, when I say I select 3 people, all 3 from here, then how many from the 7? How many from the 7? If I select 3 people and all 3 has to be from A, then how many not from A? There will be nothing from A, right? So the notation will be 5 choose 3 times 7 choose 0 over the whole thing 12 choose 3. Now that's actually the notation. But when you use calculator, you will see 7 choose 0 is 1. Okay. You can think this way. Why 7 choose 0 equals to 1? Well, suppose we have 7 items. 7 items, 1, 2, 3, 4, 5, 6, 7. How many ways can you select nothing from there? How many ways can we select nothing from there? There's only one way. And how to do it? Don't choose anything. Okay? That's why 7 choose 0, in fact, in general, not only 7 choose 0, anything choose 0 equals to 1. Okay, that's something nice to know. Now, let me modify the same question here. I still select 3 people at random. Okay, I still select 3 people at random, but I change the question. Part B, what is the probability that 2 from A? I still select 3 people though. I still select 3 people, but when I select, I get, what is the probability that I get 2 from A? Now, implicitly, it means if 2 from A, how many not from A? How many not from A? 1 not from A. Okay, so then let's take a look on the boxes. We have 5 in A and 7 not in A. This is A, this is not A. 5 here, 7 here. Now I need 2 from here, from A, and I need 1 not from A. Then how many ways we get 2 from A? There will be 5 combination 2. I usually say 5 choose 2. And then how many ways can I select 1 not from A? 7 choose 1. Over how many total ways I can select 3 items from these 12? That's 12 choose 3. Then this will be 10 times 7 over 220. That's 7 over 22. Okay, you do the next problem. I'll give you 1 or 2 minutes, maybe 2 minutes. Find the probability that I get 1 from A. So I select 3 items. I still select 3 items, but I need to get 1 from A. Implicitly, how many not from A? Implicitly 2 not from A. Okay, let me give you 2 minutes to do this problem. No decimals. If you want to make it into decimals, you can. Just keep it in 5 decimal places. Okay, but that's just purely calculator work. Hey, you want to count cards? This is the way. Okay, can anybody tell me what's your answer? The notation first. Nobody say anything. Okay, let's see. We have 2 groups, one from A and another one from B. No, I'm sorry. A from A and not A. There are 5 elements in A. There are 7 elements not in A. Now, from A, how many do I need? I need 1 from A, right? And because I need a total of 3, if I get 1 from A, it implies how many not from A? The 2 not from A. Then the notation will be, take a look here first. That will be 5 combination 1 times 7 combination 2 over 12 combination 3. Okay, now then when I use my calculator, 5 combination 1, that will be 5. How many ways can you select one element from 5? That will be 5 ways because you choose one of them, right? One of these 5. Now 7 choose 2 will be, I think that's 21. Yeah, that's right, 21. How about 12 choose 3? It's 220. So 105 over 220. If I reduce by 5, that's 21 over 44? Okay. Now 21 over 44, when I divide it, I should use 21 divided by 44, not 44 divided by 21. Okay, so in decimal, if you are interested to know what is the answer here in decimal, that will be 0.47727. Okay, and please don't forget to use your leading zero. Please don't forget to use your leading zero. Okay, but that's the probability to have one element from A. Oops, sorry. Let's get the application. The further application, counting cards. For example, a deck of 52 cards. We have 4 aces. We have 16 10 value. And the rest are not aces and not 10 value. Now, if I want to compute what is the probability for us to get a blackjack, if you remember, we did this problem before, but we did this problem using an old method. This time, we have a more advanced method. We have 4 aces. We have 16 10 value. And for the 10 values, there are card 10, Jack, Queen, King, just to remind you, right? 10, Jack, Queen, King for each one of 4 suits. So a total of 16 cards with 10 value. And then there are the rest, 32 cards for the rest. Not aces, not ace, not 10 value. Now the thing is, for us to get a blackjack, I need to get 1 ace and 1 10 value. And of course, nothing from the rest. I just choose 2. Right? Now, therefore, the probability will be 4 choose 1 times 16 choose 1 times 32 choose 0 over 52 choose 2. Now, because it is choosing 0, you can omit that. You can omit this one if you want, because we know this is equal to 1. Okay, if I continue computing this will be 4 times 16 over 52 choose 2 is 6 times 1,000, 1,326. That's 0.04827. You can check your notes from our class. You will see that this is the answer we get also at a time when we compute the probability to get blackjack. Just to remind you, at that time for us to compute the probability to get a blackjack, we did this equals to probability to get an ace first, and then face value, plus the probability to get the face value first, and then an ace. That was 4 over 51 times 60, I'm sorry, 52 over times 16 over 51 plus 16 over 52 times 4 over 51. That's how we did it at that time. Now this time we don't need to worry about the ordering. Now in the at that time we need to worry about the order ace first and then face value and then face value and then ace. Now this time we don't need to, because when we deal with combinations, the order is not important. Okay, when I get a blackjack, doesn't matter do I get an ace first and then 10 value, or 10 value first then ace, doesn't matter. As long as I get that combination, I'm good. That's a blackjack. Okay, go on further. Suppose, for example, I have 10 cookies. Suppose I have 10 cookies, and first one, they are, let's say, 5 chocolate cookies, and then 3 mint cookies, and then what else? I just make up 2 strawberry cookies. And then I want to select 3 cookies. First question, find the probability that all 3 are chocolate cookies. Second one, find the probability that all 3 are mint cookies. And the third one, let's say, find the probability that 2 are strawberry cookies. We are selecting 3 cookies, right? So if I say probability that 2 are strawberry cookies, it implies the other 1 are not. Now, what I want you to do, try to do this problem. Just use the notation. You don't need to compute them, because to compute them, you can use calculator later on. Just use the notation for this ABC, and then after that, we do harder problem. I will give you, let's say, 3 minutes for each. I mean, 3 minutes for total. So each one is 1 minute. What is the denominator first? What's the coding for the denominator? The denominator, the coding is 10 combination 3. That's right. Because we have 10 cookies to choose from, we will need to choose 3. Okay, now how about the numerator? 3 chocolate cookies. That will be 5 combination 3 times. So 5 chocolates and 5 not chocolates, right? Chocolate here, and there are 5 not chocolate. We select 3 from here and none from here, right? So 5 choose 3 times 5 choose 0, which we can omit because that's equals to 1. Remember that? Okay, so if you omit that 5 choose 0, that you're fine. Now then 5 choose 3 is, and 10 choose 3 is 120, thank you. So this is equals to 1 over 12. Now, how about if we have, we want to have 3 means? So that will be the same denominator, right? That's 10 choose 3. Okay, we still choose 3 cookies from those 10 cookies. And then how many means? And how many not means? There are 3 mean and there are 7 not mean. I need to select 3 from here and nothing from here. That will be 3 choose 3 times 7 choose 0. When I compute, I get 1 times 1 over 120. That's 1 over 120. So the probability is very, very small for me to randomly exactly selecting 3 means if there are only 3 means in among the 10 cookies. Now, slightly difficult one. What happened to this? I have 2 strawberry and how many not strawberry? We have only 2 strawberry and 8 not strawberry, right? Okay, I need to select 2 from here and then how many from here? 1, because the total has to be 3, right? We are selecting 3 items. Okay, now then the notation will then be 2 choose 2 times 8 choose 1 over and choose 3. That will be 1 times 8 over 200. 120. It's 1 over 15, I believe. Now, for the last 10 minutes, I still have 10 minutes, I believe. Let me do problems, one problem, interesting problem from the book. If you have your book with you, please open together with me. Before I pick a more actual question. Question on page 186. Page 186, right above number 13. It says there, California Fantasy 5. California Fantasy 5. The California Fantasy 5 is won by correctly selecting 5 numbers between 1 to 39. Select 5 numbers between 1 to 39. Now, you can Google it later on how to play this Fantasy 5, but basically you will select 5 numbers regardless the order from these 39 numbers. Now, the question is, what is the probability that all 5 correct? Now, our textbook answer it in the simpler way, very simple way, and that's okay for this question if you answer it the simple way. But that simple method doesn't help us to answer more follow-up questions. Okay, the way our textbook answer it as the following. Well, there are how many possible outcomes? There are 39, choose 5 possible outcomes. This is the number of outcomes. And when you use calculator, the answer will be that magic number 575,757. Okay, now of these many outcomes, how many jackpots? How many outcomes have all 5 correct? And there must be only one of them. So our textbook say this is 1 over 575,757. That's how our textbook answered it. But then the next question is, the follow-up question is, what is the probability that only 3 correct? Now, our textbook does not say anything about this type of question. Now, we will solve it in the following way. We'll solve it in the following way. There are 2 types of numbers among those 39. There are 39 numbers. How many of them correct? How many of them supposed to be the jackpot number? There are 5 jackpot numbers. Therefore, 34 of them are wrong numbers, right? So they will select 5. You will also select 5. Okay. Now, what is the probability that only 3 of what I select will match? Okay. Now, if only 3 will match, it means how many not match? 2. Because I need to select 5. That's why we call that fantasy 5, right? You are dreaming about 5 numbers, okay? And then when you wake up, you select those 5 numbers, you buy those 5 numbers. And it turns out, what is the probability that only 3 of them correct? I mean, to be honest with you, getting 3 correct is actually a big thing, a big deal. You don't need to get the jackpot, all 5 correct to win some money. No, actually, if you hit 3 correct, you get some money. And I think it's pretty big money already. Okay, now, why it's pretty big money? Because you will see the probability is very small. That 39 choose 5 at the bottom. That's the one that we will get 575,757. Okay, but what happened on the numerator? From the correct group, I will select 3. From the incorrect one, then I must select 2. I mean, I didn't know which are correct, which are wrong, right? So I will select 5 numbers. Now, what is the probability that of these numbers that I select, 3 of them happen to be correct, and therefore the other 2 must be wrong? That's the coding. Okay. Now 5 choose 3, I remember that's 10, but 34 choose 2, I don't know. $561, thank you. So this is 561 times 10 divided by 575,757. That is a small number, 0.00974. If I make it 1 over, this is 1 over 102.6 something. It means approximately out of 102 people, or 103 people to be more precise if I do rounding, among 103 people playing this game randomly, only 1 of them is expected to get exactly 3 correct. Okay, now, before I let you go, let's check with the website on Fantasy 5. Are you on my browser? Okay, now let me type California Fantasy 5. So stop thinking about that COVID-19. Let's see this Fantasy 5. Something make us happy, right? Okay, now then I will go to californialottery.com. How to play. So it shows you how to play here. I'm showing you something from website so that you know that I'm not making up number and what I teach you is usable in our daily life. Here's the number. You see? What is the probability of winning any 3 of 5 winning numbers? The odds is 1 in 103. And this 103 here is actually by rounding. Okay? It's actually by rounding. Okay, I will stop the lecture right now just to remind you things that you will have